Your checkout endpoint calls 6 services: payment, ledger, fraud, notification, analytics, settlement. One of them is having a bad day, and now nobody can check out. That's not a scaling problem, that's a coupling problem, and you cannot fix it with a bigger box. The fix is to stop calling services and start writing down what happened. Today we're building Kafka from first principles: the append-only log, partition-based parallelism, and the replication that keeps it alive when a broker dies. By the end, you'll know exactly where its throughput comes from, exactly what ordering it does and does not guarantee, and exactly which config line is silently costing people their data right now. Let's make this concrete with something UPI shaped. A payment succeeds. That single fact needs to reach 6 different places. The ledger has to record it. Fraud has to score it. The user needs a notification. Analytics wants it in the warehouse. Settlement owes the merchant money. And reconciliation needs it at end of day. The obvious implementation is the one in front of you. The payment service calls all 6. Now watch what that costs you. 3 separate ways. 1. Latency stacks. Do those calls in sequence and you've added 300 milliseconds to a payment. Do them in parallel and you're better off. But you're now waiting on the slowest one. Your P99 is whichever service is having the worst day. 2. And this is the one that actually kills you. Availability multiplies. Every service in that chain is a service that can take the payment down with it. 6 dependencies at 3 nines each gives you a combined availability of 99.4%. You went from 43 minutes of downtime a month to 4.5 hours. And not one of those services got worse. You just wired them in series. And notice what's absurd about it. The notification service can now fail a payment. A push notification is not more important than money moving. But architecturally, you made it appear. 3. Every new consumer is a deploy of your most critical service. Someone wants payment events in a new ML pipeline. That's a code change, a review, and a production deploy on the payment path. Do that 8 times and nobody wants to touch this service anymore. The root cause is that the payment service knows who cares. It shouldn't. It should know one thing: a payment happened. Who cares about that is not its problem. So we need something in the middle. And the obvious somethings are both wrong. First attempt: a queue table in the database you already have. Insert a row per event. Workers poll it. This works, and I want to be fair to it. For low volume, this is a genuinely good answer, and you should probably just do it. But watch it break, because how it breaks is the whole lesson. Every message here costs you an insert, an update, and eventually a delete. And from the last video, you already know what an insert really is: a B-tree traversal, a leaf modification, a possible page split, a write ahead log entry, times every index on the table. Then the update rewrites the row and leaves a dead tuple behind. Then vacuum has to come clean it up. You are paying full random write index maintenance price for a record whose entire life is appear, get read once, disappear. And there's a second problem. Every worker wants the oldest unprocessed row, which means every worker is fighting over the same handful of pages constantly. Skip locked keeps that correct, but it doesn't make it free. You've built a system whose hottest contention point is, by design, the thing everyone needs. Second attempt: an actual message broker. RabbitMQ, ActiveMQ, SQS. Much better. These are purpose-built, they're mature. And for a huge number of workloads, they are the correct choice. Complex routing, per message priorities, task distribution, low latency job queues. Not a strawman. But look at the data model, because it's the thing that decides the ceiling. A classic broker tracks state per message. Has this one been delivered, acknowledged, redelivered? That's mutable bookkeeping on every single record, which is random access, and it grows with queue depth. Three consequences fall out of that. 1. Consumption is destructive. Once a message is hacked, it's gone. If your fraud service had a bug for 3 hours, that data doesn't exist anymore. There's nothing to replay. 2. Fan out means copies. 6 consumers who all want every message means 6 copies of every message in the broker. Your storage and your write cost both multiply by the number of teams who find your data interesting. 3. Depth is a problem, not a feature. A slow consumer backs up the queue, and brokers holding per message state get worse as that queue gets deeper. Backlog is a pathology to be alarmed on. Stop tracking messages, track position. And that sentence is the entire pivot. If the broker never mutates per message state, all three problems evaporate at once, which leads to the data structure. Here's the whole idea. A log is an append-only, strictly ordered, immutable sequence of records. Every record gets a monotonically increasing number. It's offset. You can append to the end. You can read from any position. You cannot insert into the middle. You cannot update. You cannot delete. That's it. That is the entire data structure. And every property Kafka is famous for falls directly out of it. Property 1. Writes are appends. No traversal, no index to maintain, no page to read, modify and write back, no rebalancing. A write is copy these bytes onto the end of a file, advance a counter. And I want to be precise here because this is where a lot of Kafka explanations are quoting numbers from 2013. You'll hear sequential disk is 600 megabytes a second and random disk is 100 kilobytes a second. That was true of spinning disks. On modern NVMe, the raw gap is far smaller. Random I/O on flash is genuinely fast now. The append still wins, but for these reasons. There's no read modify write cycle. There's no index structure to maintain. The I/Os are large and few instead of small and many. And it's kind to the flash translation layer underneath. It's not magic disk physics. It's not doing work. Property 2. The broker stops tracking messages. There is no per message state anywhere. The only thing tracked is per consumer group, per partition, one integer, where you've read up to. Sit with how much that changes. Adding a seventh consumer to this system costs you one number, not a copy of the data, not more writes, one integer. That's why fanout in Kafka is effectively free, and it's the direct answer to problem 2 from the last segment. Property 3. Reads are sequential too, and mostly don't touch disk. Kafka deliberately does not build its own cache. It writes into the operating system's page cache and lets the OS handle flushing, which means a consumer that's keeping up is reading data that was written to memory a few seconds ago and is still sitting there. The disk is never involved on the hot path. Property 4. Zero copy. When Kafka does serve from the page cache to a socket, it can use send file. The bytes go from page cache straight to the network card without ever being copied into the application's memory. No deserialization, no garbage collection pressure, no user space round trip. One honest caveat that most explanations skip. TLS defeats this. If your traffic is encrypted, and in production it should be, the data has to come into user space to be encrypted, and you lose the zero copy path. Real clusters pay that. It's still fast, it's just not the brochure number. Property 5, and it's the one people underrate. Nothing is deleted on read. Retention is by time or by size, and it is completely independent of whether anyone consumed anything. 7 days of retention means 7 days of history sitting there. Addressable. So, your fraud service shipped a bug on Tuesday. On Thursday, you fix it, reset the offset to Tuesday, and reprocess 3 days of events. The bug is now genuinely undone. That is not a feature Kafka bolted on. It's what we never mutate anything buys you. One log is one file on one machine, which means one disk, one network card, one hard ceiling. Appending is cheap, but it isn't infinite. So we split the log. A topic is not a log. A topic is a set of logs called partitions, spread across brokers, each one an independent append-only sequence with its own offsets. Now throughput scales roughly linearly with partition count because there is no coordination between partitions. None. They don't share a lock, they don't share a file, they don't agree on anything. That independence is the parallelism. How does a message pick a partition? The producer hashes the record key, murmur 2 by default in the Java client, and takes it modulo the partition count. No key at all? The producer sticks to one partition until the current batch fills, then moves on. That's deliberate. Round robining every individual record would scatter your messages across every partition and destroy batching. And batching is where a huge fraction of the throughput actually lives. Let's do the arithmetic, the way we did fan-out maths last time. Take 1 kilobyte messages. Say each broker comfortably sustains 200 megabytes a second of producer writes. That's conservative on a 10 gigabit link, which tops out around 1.25 gigabytes a second. 10 brokers, 200 megabytes a second each, is 2 gigabytes a second. Divide by 1 kilobyte messages, roughly 2 million messages a second on 10 machines. That's where the headline number in every Kafka thumbnail comes from, and it's real. But here's the part those thumbnails leave out, and you should know it before you size a cluster. With replication factor 3, every byte a producer sends is a byte in, plus 2 bytes back out for the followers. 2 gigabytes a second of producer traffic is about 6 gigabytes a second of traffic inside the cluster. Kafka clusters are very often network bound before they're ever disk bound, and this is why. And for scale calibration, LinkedIn has publicly run this at around 7 trillion messages a day. Call it 80 million a second across the fleet. Uber and Netflix both operate in the same territory. So yes, the ceiling is genuinely enormous. Now let me undercut my own segment for a second, because this matters. Go back to our payments example. UPI runs somewhere around 20 billion transactions a month, which averages out to roughly 7 or 8,000 a second. Peaks are multiples of that. But even so, that is not a Kafka scale number. Kafka would not notice it. So if you're building that system, you are not reaching for a log because of throughput. You're reaching for it because of the fan out and the replay from the last segment. Throughput is the headline. Decoupling is the actual reason. If someone tells you they need Kafka for volume, ask them what their volume is. Usually the honest answer is that they need it for the other things. A consumer group is a set of processes cooperating to consume a topic, and the assignment rule is short. Each partition goes to exactly one consumer in the group, which gives you a hard limit worth writing down. The maximum number of useful consumers in a group is the partition count. 4 partitions, 4 consumers, everybody's busy. Add a 5th consumer and it sits there doing absolutely nothing. Forever. Your partition count is your maximum consumer parallelism, chosen at topic creation time. Different groups are completely independent. The fraud group and the ledger group both read every partition, each with their own offsets, each at their own pace, from one copy of the data. There's the 6 consumers, 6 copies problem from segment 2. Gone. Those offsets get committed back into Kafka itself, into an internal topic called consumer offsets. Kafka stores its consumers' positions in a Kafka topic. That pattern is going to come back in 2 minutes. Now the guarantee everyone gets wrong. Ordering is per partition. There is no global order. Kafka gives you total strict ordering within a partition. Across partitions, it gives you nothing. No global sequence, no cross-partition timestamps you can trust, nothing. And that's not a limitation they'll fix. It is the parallelism. Independent partitions are only independent because they never have to agree on order. So, the design question becomes, What needs to be ordered? For payments, the answer is per account. 2 debits on account 42 must be processed in the order they happen, or your balance is wrong. The fix is one line, key by account ID. Same key, same hash, same partition, guaranteed order, while every other account is happily being processed in parallel somewhere else. Your partition key is not a routing detail. It's a declaration of what your ordering boundary is. Choose it wrong and you'll find out in production, which is a segment we are getting to. One operational note while we're here. When a consumer joins, leaves, or dies, the group rebalances. Partitions get reassigned. Old clients did this stop the world. Everyone stops, everyone renegotiates. Modern clients do cooperative incremental rebalancing, moving only what has to move. And if you're doing rolling restarts, static membership, setting group, instance, ID, lets a consumer restart and reclaim its own partitions without triggering a rebalance at all. Those two settings turn a deploy from a latency spike into a non-event. Every partition is replicated. One replica is the leader, the rest are followers. All reads and writes go to the leader. The followers just continuously fetch from it. They're consumers of the leader's log, using the same mechanism as everything else. Kafka tracks which followers are actually keeping up. That set is the in-sync replicas, the ISR. Fall behind by more than about 30 seconds, and you're ejected from it until you catch up. Now the producer decides how much durability it's paying for. Acks equals 0 is fire and forget. Acks equals 1 means the leader has it. And if that leader dies in the next few milliseconds before any follower fetched, the write is simply gone. Acks equals all waits for every in-sync replica. So acks equals all is safe, right? Not on its own. Suppose 2 of your 3 replicas fall behind and get ejected from the ISR. The ISR now contains one replica, the leader. Acks equals all waits for all in-sync replicas. And there's exactly one, so it's satisfied by the leader alone. You've quietly degraded to acks equals 1 while your config still says all and nothing warned you. Replication factor equals 3. Min.insync replicas equals 2. Acks equals all. That's the correct set and all 3 lines are load bearing. Min.insync replicas equals 2 says, if fewer than 2 replicas are in sync, reject the write with an error rather than accept it unsafely. You're choosing to fail loudly instead of losing data silently. This is the config line I promised you in the cold open. Go and check it on your most important topic today. Because the default for min.insync replicas is 1 and an enormous number of clusters are running acks equals all with it and believe they are durable. 2 more durability details worth having. The high watermark. Consumers can only read up to the offset that's been replicated to all in-sync replicas, which means you can never consume a message that might still vanish in a failover. Consumers are structurally protected from reading data that isn't committed yet. Unclean leader election. If every in-sync replica is down, should Kafka promote a stale replica and keep serving, accepting that committed messages disappear? The default is no. It stays unavailable rather than lose data. That's an availability versus durability dial, and the default is the right one for anything financial. Now, one update, because if you learned Kafka from a tutorial more than a couple of years old, you learned something that is no longer true. ZooKeeper is gone. Kafka used to run a second distributed system alongside it just to store cluster metadata. Who's the leader of which partition? Which brokers exist? What topics are configured? 2 systems to operate. 2 to tune. 2 to page you at 3 a.m. That's been replaced by KRaft, Kafka's own Raft implementation, running in a quorum of controller nodes. It went generally available in the 3.3 release, and Kafka 4.0 removed ZooKeeper entirely. There is no ZooKeeper mode anymore. And here's the detail I love. Where does KRaft keep cluster metadata? In an internal topic called cluster metadata. It's a log. Brokers don't get pushed updates. They consume the metadata log and apply it. Exactly like a consumer replaying events. Kafka stores consumer positions in a Kafka topic. Kafka stores cluster metadata in a Kafka log. The same structure we spent this whole video building is the one the system uses on itself. That's not a gimmick. It's what it looks like when an abstraction is actually the right one. Practically, it buys much faster failover and it raises the ceiling on partitions per cluster by orders of magnitude because metadata propagation stopped being the bottleneck. This is the half of the conversation that separates people who've read about Kafka from people who've been on call for it. 1. You cannot have global ordering and parallelism. Need every message in one strict sequence. That's one partition. One partition is one consumer, one broker, one disk. You've thrown away the entire scaling story to get it. There's no clever config. Pick your ordering boundary as narrowly as you can, key on it, and let everything else run in parallel. 2. Repartitioning breaks key affinity. This one bites hard. Partition assignment is hash modulo partition count. Change the count and the mapping changes. Account 42 used to land in partition 2. Now it lands in partition 6, while its entire history is still sitting in partition 2. Two partitions now hold that account's events, with no ordering relationship between them. And you can add partitions, but you can never remove them. So the practical advice is over provision partitions at creation time, because it's the one number you can't walk back, which runs straight into 3. Partitions aren't free. Each one is file handles, memory for producer and consumer buffers, an entry in cluster metadata, and its own replication streams. More partitions also means less data per batch, which means worse compression and higher end-to-end latency. KRaft raised the ceiling a lot. It didn't make the per partition cost 0. Over provision means 2 to 3 times your expected consumer count, not 1,000 partitions on a topic doing 40 messages a second. 4. Delivery semantics. And the part that gets misexplained. Default behavior is at least once. On a crash between processing and committing your offset, you reprocess. Duplicates. Kafka does have exactly once. Idempotent producers plus transactions since 011. It's real. But here's the nuance almost nobody states. It's exactly once within Kafka. It covers consume transform produce, Kafka to Kafka. The instant your consumer writes to Postgres, calls a payment, API, or sends an email, you are back to at least once, because that system isn't in the transaction. Make your consumers idempotent. There's no config that does it for you. Dedupe on an event ID, upsert instead of insert, make the operation naturally repeatable. That's the work. And exactly once isn't free either. Transaction coordination costs throughput, and readers in read committed mode can't read past the last stable offset. So you're adding latency too. 5. Hot partitions. Key by merchant, and one merchant is 40% of your volume. 40% of your load is now on one partition, on one broker, consumed by one process. Adding partitions does not help. The hash sends that merchant to exactly one of them regardless. The mitigation is a composite key, merchant plus a bucket number, spreading them across several partitions. And notice the cost. You just gave up strict ordering for that merchant. Skew and ordering are in direct tension, and there's no free version. 6. Kafka is not a database. The only access paths are offset and, indirectly, timestamp. There is no give me all events for user 42. To ask questions, you materialize the log into something that answers questions. A Kafka streams state store, Postgres, Elasticsearch. Log compaction gets you key to latest value, which is a change log, not an index. 7 and the one I'd actually lead with. You probably don't need it. A Kafka cluster is a real distributed system with real on-call wait. At low volume, SQS, pub, sub, RabbitMQ, or the Postgres queue table from segment 2 will serve you better and wake you up less. Reach for the log when you need fan out, replay, or retention. Not because it's on the architecture diagram you liked. Two things worth knowing for 2026 since this ecosystem moved recently. Tiered storage. Recent segments stay on broker disks. Older ones get offloaded to object storage like S3. It went production ready in the 3.9 release and it changes the economics completely. Retention stops being a function of how big your broker's disks are, so months of history becomes genuinely affordable. It also makes scaling cheaper because there's far less data to shuffle when you add a broker. And queues for Kafka share groups Cape 932 arrived in early access in 4.0 and has been maturing since. It lets multiple consumers share a single partition with per message acknowledgement, which is essentially Kafka growing the one thing RabbitMQ had over it. Check its current status before you build on it. So, the mental model to walk away with. Kafka is not a message queue that got fast. It's a distributed, replicated, append-only log. And every single property comes from that one decision. Appends instead of mutations, so writes are cheap. Position instead of per message state, so fan out costs an integer. Nothing deleted on read, so replay is free. Independent partitions, so throughput scales. And because they're independent, ordering stops at the partition boundary. And notice the through line from the last video. A B tree was a search tree redesigned around the cost of a disk strip. A log is a queue redesigned around the cost of a random write. Different problems, same discipline. Stop designing around the abstraction and start designing around what the storage actually charges you for. Which brings us back to the one I still owe you. Buffer writes in memory, flush them sequentially, merge in the background. That's an LSM tree, and it's the same instinct as this log applied inside a single database. Cassandra, RocksDB, every modern time series store. That's the next one. Your homework, two things, both take 5 minutes. Check the consumer lag on your most important topic. That's the log end offset minus your committed offset. And it's the one number that tells you whether your system is keeping up. Then go look at min.insync.replicas on that topic. If it says 1 and your producer says acks equals all, you have a durability bug in production right now. I am Dhruva, this is the Tech Intern. See you in the next one.